recall what we had done. The first step we did was we looked at finite measure, okay, and then F bounded measurable. We looked at this special case, okay, and then we defined this, okay, first of all F bounded, okay, then we said that the Lebesgue lower of F and the Lebesgue upper of F are equal if and only if F is measurable. And therefore, for those functions, this common value is defined as the integral. So, F measurable, bounded, mu e finite, we define integral F d mu. Any one of these we can choose, which is the lower bound, which is the supremum of phi less than or equal to F, phi simple, integral E phi. And this satisfies the standard properties, namely integral of F plus G over E is integral over E of F plus integral over E of G. Integral E alpha F is alpha integral E F. 3 F equal to G almost everywhere means integral F is equal to integral G. And the monotonicity, if F is less than or equal to G, implies integral E F less than or equal to G. Whenever I write something, it's enough if it holds almost everywhere. Okay, so these are minimum standard properties of integrals which all hold. Of course, all these F and G are of this type, bounded, G is the measurable. So then we had the basic convergence theorem, which we call as the bounded convergence theorem. Which said that again mu e is finite, Fn, F measurable, there exists M bounded measurable. Okay, so I'll put it this way. There exists M such that mod Fnx less than or equal to M for every N for every X. There exists a real number M. Okay, that is what boundedness is taken care of. All and Fn tends to F almost everywhere. So if you have a sequence of bounded functions, uniformly bounded functions, the same bound M works for all the functions at all the points. So if you have a sequence of functions which are uniformly bounded on a finite measure space and if that sequence converges, then the integrals will also converge. That is the first convergence theorem we had. Okay. So that gives us a clean picture of finite measure spaces and bounded functions. And obviously, since we are taking the supremum over simple functions and step function collection is smaller than this, we automatically get anything that is Riemann integrable is also Lebesgue integral. So, in particular, if E is equal to a finite interval, then F Riemann integrable over AB implies F Lebesgue integrable over AB, and integral Riemann is equal to integral Lebesgue. Okay. That's the, so therefore, Lebesgue has completely taken care of Riemann. Then he makes the further moves. Next he says, let us drop, that is the second, drop the condition mu e is less than infinity. So now we are going to look at general measure space. Okay, it can be finite measure or infinite measure, we don't care. So E measurable, mu e may not be less than infinity. May or may not. so we don't care now. Okay, that hypothesis we don't ask. But then we are now going to take f slightly, even bounded we will drop for the time being. We will say f is non-negative. At almost everywhere also is enough. In other words, basically we are trying to say the graph can be split into two parts, the upper part and the lower part, and therefore we can deal with positivity is enough, because the lower part can be flipped up and looked at as the positive part. So we are going to look at non-negative functions measurable. So now we are going to look at how we can define the integral of non-negative functions, but over any measure space. It could be finite or infinite measure space. See, previously we first had defined only integrals of simple functions. So we started estimating them through simple functions. Now we already have better things in our arsenal. We know how to integrate bounded functions on finite measure space. So we use them to estimate. Okay. So therefore, what we do is we define the integral of f over the set E to be, okay, let me use some notations to write it in short form. Okay. We must bring things back to this level. See, previously we had simple, we took this to the simple level. Now we have this, we bring this to this level. To bring this to this level, we must look at, in place of phi, we must look at functions which are of this type. Okay, so therefore we will define B to be the set of all functions from E to R such that bounded measurable, and also I want to deal only with finite measure. So the E may be an infinite measure. So I want H to be non-zero only on a finite measure set. So that outside it is zero, we don't care. So therefore, the set of all and the set of all x in E such that Hx not equal to 0 as finite measure. See, so I am going to consider all those functions which are defined on E but are of the previous type. Okay. So now, therefore, we can define integral EH for any H in D. Because they are non-zero only on a finite measure, so only integrate over that finite measure set. They are bounded, everything is taken care of. So now we are going to look at BF to be all those functions H in B which are less, which are given underestimates. Okay, that's what we are going to do. So now the integral of H is an underestimate of F. Integral of F, take the best underestimate, that is the supremum of the least upper bound, that is defined as the integral. We define integral of F over E to be integral H over E, the supremum over H belonging to BF. Okay, all the H's which are underestimating F, their integrals, and take the best of all those underestimated integrals. This is how the integral of F is defined. Okay, I don't write d mu, etc. for short form. Okay, so that gives us a definition of the integrals, but we must make sure. But all this is also part of it, because we are saying mu may be or mu may not be. If mu is infinite, it is of this type. So this gives a definition and this gives a definition. Both must agree. So that is the first thing we say. Whenever mu is less than infinity and f bounded, this agrees with step 1. That's easy, because integral f itself is one of the underestimates there. Okay, therefore, we have already got the best underestimate. 2, all the standard properties, 1, 2, 3, 4 hold. The linearity, everything gets carried. Okay, 1, 2, 3, 4 hold for such f. Such fg means non-negative measurable functions. So we have pushed our definition to non-negative measurable functions. Now once we push the definition to non-negative measurable function, we look at convergence theorem at that stage. At every stage we look at the convergence theorem which allows you to interchange the integration and the limit. So next we look at convergence theorems for these. At the second stage. Well, in all these convergence theorem, I'll write first a very fundamental, it's a part of a proof of the theorem, but it is definitely separated out as a separate lemma. And the theorem has some name and the lemma has another name. Okay. So now I take Fn greater than or equal to 0 and Fn converges to F almost everywhere. Okay. So I want to know whether integral Fn converges to integral F. It may not even converge. So what is it that we can best say? Let us go through this for a while. Okay. So now what I am going to do is, I am going to define a new function. You will see. I am going to reduce it somehow or the other to this case because our theorems will be pulled back to the lower level convergence. So I am going to define an Hnx. To apply that, I must have a bounded function, etc., etc. And so therefore, okay. Let me first. Now I look at BF. What is BF? All those bounded functions which are non-zero only on a finite measurable set and are dominated by F. Remember, BF is all those functions which are bounded, they are non-zero only on a finite measure set, and H is less than or equal to F. They are dominated by F. So now take any H. Now define Hnx to be the minimum of Hx and Fnx. See, thereby that I replace the old sequence Fnx by a bounded sequence now, because Hnx cannot exceed H, and H is not only bounded, it does not vanish only on a finite measure. So from the given sequence Fn, I am concocted a sequence Hn which comes to our level where we know how to handle convergences. Okay, so now check. Easy, it's not very, not at all difficult. Hnx converges to Hx. Okay. See, the possibilities are F is here, H is here, and Fn is here. Okay. If Fnx is below this, then Hnx is this. But since Fn is pulling to F, Hnx will go to this. But it cannot cross H. Therefore, H must have coincided with F at that point. So obviously, therefore, Fnx converges. If H is on this side, then Hn is H itself and it converges to H. So anyway, Hn converges to H. So just the simple picture, you will see that at any point Hnx will converge to Hx. So now I can apply, see, Hns are bounded. Hns are non-zero only on a finite measure set. H is the same. So all the conditions of bounded convergence theorem are satisfied. Why they are satisfied? Hn is dominated by H and H is bounded. So one bound can be found for all the Hn. So Hns are bounded because Hnx is less than or equal to mod Hx less than or equal to some m because H is bounded. So therefore, by bounded convergence theorem, see, therefore I always pull it back to a theorem which I know. By bounded convergence theorem, integral Hn converges to limit of integral Hn is equal to integral H. Okay, so let me call it as some star. Okay, I'll write here itself. Now compare Hn and Fn. So I have to now from here on some over the other, let us look at, so I will write it as, I will have to now bring in Fn somehow. See, my eventual result must be in terms of Fn. Give me Fn, I will go to my comfortable zone of bounded functions, etc. Get a result. From my comfortable zone, now I have to come to the uncomfortable zone of the Fn's. Okay. So now I observe the Hns are less than or equal to Fn. Right? Because Hn is the minimum of H and Fn. So Hn cannot exceed Fn. So if Hn is less than Fn, the integrals are monotone. So therefore integral Hn is less than or equal to integral Fn. And therefore infimum of this is less than or equal to infimum of this. Therefore lim inf will be less than or equal to lim inf of this. Limit of the infimum of Hn is less than or equal to the limit of the infimum of the Fn. Okay. This is smaller than this, so beyond any state the infimum of this will be smaller than that. Then take the limit, so the limits will be smaller than this. So the lim inf, I know lim inf always exists. Okay, if you recall, we proved that. So lim inf always exists. The limit of the infimum is less than or equal to the limit of the infimum of this. But integral Hn exists. The limit of the integral Hn exists. So lim inf will be exactly equal to limit. So this is equal to, whenever the limit exists, the lim inf, the lim sup, all are equal, and the limit are all are equal. So that is equal to limit Hn, but that is equal to integral H. So what we have got is integral H is less than or equal to lim inf Fn for every such H. Okay, so let me write. Okay, let me write it here itself. Where is the duster? No, this is not the right thing. These dusters are confusing. Some more whiteboard, some more. So therefore, what we have got is integral H is less than or equal to lim inf of integral Fn for every H in Bf. We have taken any H in Bf and eventually found that integral H is less than. Now, the integral of F is defined as the supremum of all these integrals. Since every one of them is less than or equal to this, the supremum of H belonging to Bf of integral H is less than or equal to lim inf of integral Fn. But that is precisely the integral of F. So integral of F is less than or equal to lim inf. So the limit of the integral of the limit is less than or equal to, because we don't even know whether the limit of the Fn exists, so at best we can say it is less than or equal to the lim inf of Fn. This is called Fatou's lemma. Okay. It is little better, you can do it a little better than this, but I will use only this much. Okay. So this is called Fatou's lemma. That is the first convergence theorem about positive non-negative functions. I met one old student of ours who is now a faculty in IIT Madras, who was in CEDT early, about 10, 12 years back. And he said that I have your full video lectures on the analysis course you gave at that time, but in that the proof of Fatou's lemma is missing. So I told him, you wait, you will upload today's lecture, you will find proof of Fatou's lemma. That now we have proved the Fatou's lemma. So Fn non-negative, Fn converges to F almost everywhere, implies integral F is less than or equal to lim min of integral Fn. Okay. And in particular, if this integral Fn converges, then integral of the limit is the limit of the integral. That is always guaranteed. If the sequence of the integrals converge, then automatically lim min will be equal to the limit. So integral of the limit is less than or equal to the limit of the integral is what we can say. Okay, so this is a sort of a base for the convergence theorems that we'll be proving from now on. So now what we do is we push further. Suppose Fn's are increase or non-decreasing to F. We are simply saying that Fn converges to F almost, but if they are coming from one side, that Fn's are all non-decreasing. So that is Fnx less than or equal to Fn plus 1x. I'm sorry. Yeah, Fn plus 1x almost everywhere for every n. So they are all converging, but they are non-decreasing. So and Fn converges to F almost everywhere. This is what I meant by saying this thing. It is non-decreasing and it converges to F. So suppose I have that, then we have Fn is less than or equal to F. Because they are all going up, Fn's are all going up to F. And therefore monotonicity will say integrals Fn's are less than or equal to integral F, and therefore the lim sup of this will be less than or equal to integral of F. Because for every n this is true. The supremums are less than or equal to F, the limit of the supremums are less than or equal to F, and so on. So the lim sup is less than or equal to integral F, which on the other hand, without any hypothesis, was less than or equal to by 40. But now lim sup cannot be more than that. So this is less than or equal to lim min of integral F. The lim min is always less than or equal to lim sup. So now all of them must be equal. That means lim min is equal to lim sup, the limit exists and is equal to integral F. So that says when that we can conclude that that integral exists, at least some condition. So therefore integral Fn converges and equal to integral F. That is called the monotone convergence theorem. Fn greater than or equal to 0, Fn non-decreases to F almost everywhere, implies limit integral Fn is equal to integral limit Fn. That integral limit Fn is F. Okay. So that is the one other theorem where you have this process of interchanging the limit, and all these are invalid in Riemann integrals. Lebesgue got them all nicely. Okay. Not necessarily true in Riemann integrals, even with this monotonicity condition. So Lebesgue then he moved to a general measure that was the second stage. From finite measure we went to infinite measure, but we restricted to non-negative functions. Then he makes his final move. General measure, general function, may be positive, may be negative, I don't care. It may be taking both positive and negative. That is the third stage of his construction. Third stage says E measurable, F measurable. And of course here he makes one comment we'll make. We say, I will only do this, F greater than or equal to 0 is integrable if integral F is finite. That integral F could be infinite because we never know, because of the measure could be infinity. The integral could, it may be a constant function, one at all the points. So the integral could be infinity. So we say integrable if integral F is finite. We are interested only in such functions. Okay. So in this case, what he does is he defines two functions. That is, the graph which is above, which is the maximum of fx and 0. If it is positive, you take that value. If it is negative, just take the 0 value. In other words, you simply eclipse the graph of the function below the x-axis. And similarly, f minus, what it does is you flip the graph and then eclipse again the bottom. So flipping the graph boils down to minus fx and again taking the maximum. So the trick is now both are positive functions. So now back to this situation, okay. So both note 1, f plus x, f minus x are greater than or equal to 0. So back to, see, it goes step by step, it climbs one step and then pulls that result to the next step, and so on, okay. And 2, fx is equal to f plus x minus f minus x, and 3 mod fx is equal to f plus x plus f minus x, because the negative must be brought to positive. Now this says can define integral f plus and integral f minus, because both are non-negative. Now we will have to define the integral of f, keeping in mind the linearity that asks as integral f plus minus integral f minus. But then this could be infinite, so there will be problem. So we take those functions which are, for which these are finite. We say f is integrable. Of course, we can do a little better than this, but this is the main thing. If f is integrable, if integral f plus is less than infinity and integral f minus is less. If you can define the integral, if one of them is finite, that's enough. But we say the word integrable. Okay. The integral can be defined if one of them is finite, but integrability requires both of them finite. And define integral, then define integral f as integral f plus minus integral f minus. Now I've got the integral of a general function, okay, and again all those, this will not lose what we have got. When you have only a positive function, you will have only the f plus part and you will get exactly what you had before. So at each step you are not losing what you had already, but you pull up more functions for integration. First we had only simple, and then we had bounded, finite measure, we pulled up. Simple came along with you and their definition didn't change. Then you went to non-negative, nothing changed. Then you now went to the general function. The previous fellows don't change. So all properties hold. Okay. All properties hold. What does all property mean? Linearity, monotonicity. If f is equal to g almost everywhere, then integral f is equal to integral g. Now, this is the final convergence glitch, okay. So now, I have to prove a convergence theorem for such integrals, for the general integrals. So that is the convergence theorem. So now I have E, any measurable set, and then Fn greater than Fn measurable functions, integrable functions. Okay, let me say measurable functions. Fn converges to F almost everywhere. I wanted to question this, whether integral Fn will converge to integral F. Now, if you look at bounded convergence theorem, even there we wanted to put some additional hypothesis. We wanted that all the Fn's are bounded by one constant m. Why did we want that constant m? If you recall, let me recollect the bounded convergence theorem is a clue for the hypothesis that you need. In the bounded convergence theorem, we said mod Fn less than or equal to m for every n for every x. The reason for that was we wanted to look at integral E Fn minus f. This is what we wanted to estimate. We wanted to show that this can be made small as n goes to infinity, because, okay, first we wrote, you look at mod, I want to show that integral Fn converges to integral f. So I want to look at the difference. I want to show that this can be made small. But this is, so therefore I will show that this is small. What I did was, if Fn converges to f uniformly, then this is automatic. So now since Fn converges to f almost everywhere, except on a set of small measure, I can make this converge uniformly. So I will write it as integral E1 mod Fn minus f plus integral E2 mod Fn minus f for E1 complement, where Fn converges to f uniformly on E1 and measure of E1 is less than delta. Right. Now therefore, uniformly this can be made small. So this part is less than epsilon, some epsilon 1 times the remaining is the measure of E. Okay, this part is less than epsilon, so the integral will be less than epsilon times the measure of E1 for large n by uniform convergence. That part can be taken, because for all x I can make Fnx minus fx less than epsilon uniformly. So therefore I can pull that out, and the remaining t integral over E1 will give you just the measure of E1. And this part, you see, because Fn and f are bounded by m, I can dominate this by 2m, right? I can dominate this by 2m, because that is less than or equal to mod Fn plus mod f. All of them are less than or equal to m. So that whole thing can be dominated by 2m. So that is less than or equal to 2m times measure of E prime, which is delta. So that is 2m times delta. So choose the deltas and the epsilon ones, so that this whole thing becomes less than epsilon, and you have got the uniform convergence. See, the problem here is this mu epsilon prime was finite. Why? Because the Gagarov's theorem was valid only on a finite measure space. This sort of splitting I can do. But in the infinite case, I don't know, this remaining part could still be large, and therefore this could become infinite, 2m times infinite. So that m, that integral of that m were not very good. It could become infinite in this case. So therefore, instead of constant, I will dominate it by a function whose integral is finite. So that's what the condition here is. There exists G integrable such that Fn x is less than or equal to Gx for every x. I don't know whether I want modulus. Okay. So these conditions, then we will prove this. This is called Lebesgue's dominated convergence theorem, LDCT. See, the conditions are essentially like bounded convergence theorem. Measurable set, there I have finite. There I had measurable bounded functions, I have measurable functions. Fn converges to f, ever must everywhere. There I had dominated the fn's by a constant. That was enough for me because everything was finite measure. Constants are integrable over finite measures. But I don't have constants are not integrable over finite measures. So therefore I will dominate instead of a constant by a function whose integral is finite. So if I had only taken a constant, integral over m over e will be infinite, because if measure of e is infinite. So to avoid that, I replace it by a function whose integral is finite. That is integrable function. Then limit integral f, which is the limit n tending to limit n tending to integral fn is equal to integral limit fn, which is the same as integral f. So I want to show that the limit and this thing can be interchanged. This is the final clinch on the exchange of limiting process and the integration process. So all you need to do is, all you need to have is all these functions, or one fellow is blocking them all, and that fellow is good. He has a finite integral. Then everything works out. Okay. So how do we do this? It's very simple. Okay, now you see this will, because this looks similar to bounded convergence theorem, it will it will go back to one of these theorems. Okay, basically you will use all of them. Okay. So I have mod fnx less than or equal to gx. What does that mean? Minus gx less than or equal to fnx less than or equal to gx. Okay. Now this says gx minus fnx is greater than or equal to 0, and gx minus fnx tends to gx minus fx, because fnx converges to fx. So let's call it as some hn, and so hn converges to h. Right? So I have a sequence of non-negative functions. See, I have now a theorem for non-negative functions. I am going to go pull these things to non-negative function. I have a sequence of non-negative functions which converge almost everywhere to this function. Then Fortis lemma says, what is Fortis lemma? Integral gx minus fx. What was Fortis lemma correctly? Integral f is less than or equal to lim inf of, this is okay, hx is less than or equal to lim inf of hm. This is what h is less than or equal to lim inf of hm. Let's write that in full. Integral g minus integral f, everything is now finite because they are all been dominated by an integrable function, less than or equal to lim inf of g minus fn. So integral g minus integral f is less than or equal to, this has nothing to do with n, so that will come out as integral g. Lim inf of minus is minus lim sup. Okay, so this is equal to minus lim sup of integral fn. So compare these things, you get lim sup, g gets cancelled, that's finite because integrable, so you can cancel finite things. So lim sup of integral fn is less than or equal to integral f. Take this to this side, and they cancel the g. Okay. So this is what we get by using this part. Now use this part similarly. G plus fn is greater than or equal to 0 and converges to g plus. Apply the same for 2. What does Fortis lemma gives? The limit of this is less than or equal to lim inf of the integral of g plus fn. Again, the same Fortuit's lemma is applied to this. So once again, this is integral g plus integral f less than or equal to integral g. Now no more minus, so it is just a lim in integral f. Cancel the g's, so we get integral f is less than or equal to lim in of integral f. Now lim sup cannot be less than or equal to lim in, so that's again equal. So it implies less than or equal to lim sup integral fn implies limit integral fn exists and equal to integral f. That is the dominated convergence theorem. So basically, therefore, you can have any kind of functions as long as there is one fellow who is controlling them all from the point of integrability, then you can interchange the limit and the integration. So all the problems that Riemann had about this limiting process of integration, Riemann had several problems. One was, even though I had a sequence of functions which are Riemann integrable, and even though they converge to f may not even be Riemann integrable. That was his first problem. The second problem was, even if it was Riemann integrable, the limits may not be possible to exchange. Even if they are dominated, the limits may not be exchangeable. But all that Lebesgue removed. He said, limit must be measurable, therefore this integral is defined. And under reasonably good conditions, the limiting processes can be exchanged. The limit and the integral can be exchanged. So the fundamental theorem is the Fortuit's lemma. One of the fundamental theorems is Fortuit's lemma. From that follows monotone convergence. From that follows this also. Okay. So and for monotone convergence theorem, we also use the dominated convergence. So the bounded convergence. The bounded convergence theorem and the Fortuit's lemma are at the base of all the things, because they are the simplest levels. One takes care of bounded measure, bounded functions. Other removes the boundedness of the measure but allows non-negative functions only. Together, they are able to handle all types of convergences. So, Lebesgue integral, therefore, is a far-reaching generalization of the Riemann integral. Everything Riemann integrable is Lebesgue integrable, but Lebesgue can integrate over arbitrary measurable sets. Lebesgue can integrate over arbitrary functions. They may not be bounded also. Unbounded functions also he can integrate. He can interchange the limiting process and the integration under the suitable conditions. So, wherever you have a measure, you can carry out the same process. That's why I wrote d mu. Okay, it did not matter whether we are working in real. The set E was a subset of the real numbers or what. The E is a measurable set. That's all. It's some in general measure space, and F is a real valued functions. All these functions are real valued. So you may have a general omega, a general sigma algebra, and a general measure, and you may have a function f omega to r. You can do all this and define the integral. So now we can do a lot more than what Riemann did. Nothing to do with real line, nothing to do with real numbers, an arbitrary set, arbitrary sigma algebra, arbitrary measure, and your functions, you can integrate them. So Lebesgue's integration just swept the field of analysis with this tremendous generalization of the notion of integration. And he has this major convergence theorem. I think that's the right place to stop the course. We have the main integration, we have the main convergence theorems, and of course, the course, the subject never ends. If you want to go further than this, then come the basically the so-called the beginnings of functional analysis, the classical Banach spaces, namely the LP spaces. Okay, those are special types of functions for whom certain types of combinations are integrable. Okay, and they give you a beautiful structure of Banach spaces, and then the study of these are all concrete examples of the abstract notions of Banach spaces, and most of analysis is done in these Banach spaces. Okay. But that's a different ballgame. Okay, probably quite a bit of it you will find in that functional analysis lecture notes. So basically, therefore, the first course in real analysis is abstract set theory, real number construction, standard functions like continuous functions, then the Lebesgue measure, Riemann integration, Lebesgue integration, convergence theorem. I think this is the right time. We'll stop the course. Right time also, because next week exams start. If there is anybody busy with courses and all that. So I'm very happy that the number of students did not converge to 0. Okay, we were non-zero convergence. I think you can upload all the lectures. If you have any questions, you can always send me a mail. I'll be happy to answer. Thank you.